Today we're talking about compound events, and we're going to find the probability of events that are called mutually exclusive and inclusive. So is mutually exclusive a phrase you may have heard before?
Yes.
Okay, because sometimes people use it in everyday life. They'll be like, well, they're not mutually exclusive. You know, because people be like, well, I can't because of this. And it's like, well, you could do both, right? If they're mutually exclusive, that's going to be something where you can't do both, okay? So it would be like if you're tossing a coin, you can't roll heads and tails on the same coin toss, right? And then the other examples on your sheet is you can't roll a 1 and a 2 if you're only rolling one die, if you're doing a number cube experiment. So in terms of a Venn diagram, mutually exclusive events, they never overlap each other. I wrote on the board what you usually see in terms of a Venn diagram. Do you guys do Venn diagrams in English sometimes?
Yeah.
Or other classes? Like in one, you put everything of this character. And then in the second one, everything that goes with character B, and then in the middle is what they have in common. Okay, so mutually exclusive, it does not have anything in common. And then there's this symbol that's a U for a union. Okay, and a union, that symbol just means or. So the reason why it's a U is it means the union, which is or. Sometimes you go over this when you're talking about the sets. But I know you guys had some interesting middle school years because of pandemic stuff, so that may have had to been cut out. Have you guys seen the U for union? What's that? It's not really a domain, it's like an intersection of sets. Like you have a set of numbers, 1, 2, 3, 4, 5, and then you have another set of numbers. They would look like this. They'd be like, oh, you have 1, 3, 5 in one set. In another set, you have 1 and 3. And then you'd have to find the union between them. Or you'd have to find the intersection between them, which we are going to talk about that as well. So for the first example, we have a cute little nurse here. And a group of students is donating blood during a blood drive. A student has a 9 out of 20 probability of having type O blood and a 2/5 probability of having type A blood. So the first thing you just have to explain is why they are mutually exclusive. Okay, why can't they happen at the same time, right? What's true about our blood? Yeah, you can only have one blood type, right? Do you guys know your blood type?
Negative.
I should ask your green. Are we green for St. Patty's Day or for MSU? Okay, so a person can only have one type of blood. So yes, that's why they are mutually exclusive. A person can only have one type of blood. All right, now we're going to find the probability that a student has type O or type A blood. Okay, so they have type O or they have type A. So we are going to use this equation, okay, the probability that they have type O or type A. So I like to write out what they are in words. So the probability that they have type O or type A, all we have to do is find the probability that they have type O plus the probability that they have type A. And then that's given to you in the problem. So what's the probability that they have type O? 9/20. What's the probability that they have type A? Okay, so we're just going to add those together. But of course, if you were going to add two fractions together, what do you need to add the fractions? Yes. Okay, so how do we get the common denominator? 2/5, top and the bottom, okay, by 4 over 4. If you multiply by 4 over 4, then you will get 8 over 20, and then you can add. So, as a reminder, adding fractions, add the numerators, denominators do what? Stay the same. Okay, so that's going to stay 17 over 20. Okay, so you do have to know how to, what you do, you have to make sure you get the common denominator and then know how to add fractions. All right, the other type of event that we're going to talk about today are inclusive events. So those are events that have one or more outcomes in common. Okay, they have one or more outcomes in common. So an example of that would be rolling an even number and rolling a prime number. Because you can roll an even number that's prime, there's only one even number that's prime, and that's what? 2. Okay, so if you do the Venn diagram for this, there will be an overlap. Okay, and then I put a little diagram on there for you so you could see the overlap numbers. Okay, so on a number cube, the even numbers are 2, 4, and 6. The prime numbers are 2, 3, and 5. And the one that is both even and prime is 2. So in order to find the probability, okay, again you have this union symbol that means or. Okay, this means or. So the probability of A or B happening is you take the probability of A, add it to the probability of B, which is the same exact thing that we did above, but now you have to minus that overlap. So this means the intersection of A and B. Okay, so you're going to have to subtract the overlap. And the reason why is because it's being counted twice. It's being counted in the probability of A and the probability of B, right? Because 2 is in both of these circles, really ovals. Okay, so because it's counted twice.
At this time we are conducting our tornado drill. Please go to your safe space. Thank you.
Where's our safe space?
All right, so we're gonna pick up at example 2. So what we just learned is how we are going to subtract the overlap. Okay, so when they happen at the same time. So if you're rolling a 4 or an even number, all you have to do is find the probability of rolling a 4 plus the probability of getting an even number and subtract the probability that it's 4 and even. Okay? Now, because this is a number cube, how many total sides are there? 6. Okay, so the total is 6 sides. That's going to be your denominator every single time. So how many sides have a 4 on it? Just 1. So the chance of rolling a 4 is 1 out of 6. Okay? How many evens are there on the cube? 3. So it's 3 out of 6. Keep it as 3 out of 6 so that you have a common denominator. Okay, what side is 4 and even? Only the 4, right? It couldn't be a 2 and be even in 4. So you're going to subtract the 1 over 6. So 1 plus 3 is 4. 4 minus 1 is 3. 3 over 6 reduces to 1/2. 1/2 is your probability. Okay, so based on that, I want you to do B. Okay, based on that, I want you to do D. So rolling an odd number, probability that the number is odd, plus the probability that the number is greater than 2, and then minus the probability that it's odd and greater than 2. And I feel like we're pretty good at the odd and the even, right? Because how many odd numbers are there on the cube? 3. Okay, so 3 of the 6. Same thing with the even. Now, if they're greater than 2, let's list those out. What numbers are greater than 2? 3, 4, 5, 6. How many choices is that? 4. So it'll be 4 over 6. And now we got to subtract the overlap. So which one of these are odd? Yep, number 3 and 5. So there's 2 of the choices. Okay, those are odd and greater than 2. Okay, so 7 minus 2 is going to be 5. Okay, so then try this one. Rolling an even number or a number greater than or equal to 5. Sorry, is this bothering you guys? If it's bothering me. A little heart. Please don't have. If you know how to draw a heart, you know how to draw a shamrock, right? Yeah, it's just a heart here, heart here, heart here, heart here. Oh, so you have. You have to.
I missed it. Actually,
That's sad. Yes, please do not. I already had to deal with that today. You think?
Oh, pinching? Where's it I'll call it.
Hey, keep your ears to yourself.
Oh, that's okay. What is it? I gotta call the principal.
Alright, so let's do this one. Yeah, do the even and then the numbers greater than 5. Okay, so like I said, I feel like you're really good at the even, and then if you're having trouble, let's just list these out. What numbers on a number cube are greater than or equal to 5? 5 and 6. So how many options is that? 2. Okay, so once you've already done this and you've listed them out, all we have to do is look at this list and see which ones are even and greater than or equal to 5. Yeah, only this one, right? So this is the even one. So minus 1 out of 6. Okay? Now, if you're ever confused on which equation to use, like if you're not sure if you just add or if you add and then subtract, you can always use the one where you subtract the intersection, because if they're mutually exclusive, what would the number on top be? If they don't overlap, if they can't happen at the same time, they'd be 0, right? So if you subtracted 0, that wouldn't make a difference. And then, of course, always reduce your fraction, okay? All right. The next type is applications. So for our next example, this is of 1,560 juniors and seniors surveyed. 840 were seniors, and 630 read a daily paper. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? Okay, so the first thing we're going to do is set up how we're finding the probabilities. So it's a senior or read a daily paper. So we first find the probability of being a senior. We're going to add that to the probability that they read a daily paper. Bless you. And we're going to subtract the probability of seniors who read the paper. Okay, now they do tell you the total number of students, right? So this is going to be your total number, so this is going to be your denominator. And it's going to be your denominator for every single one. So the 1560 minus, and then on the bottom you have the 1560s. Are the number of seniors identified in the problem? Yeah, how many? Yeah, 840. So that we can plop right in there. What about the number who read a daily paper? 630. Okay. Now, does it explicitly tell you how many seniors read the paper? No. It explicitly tells you how many were juniors, but we can calculate it by doing just some simple math, okay? So it says 215 of the paper readers were juniors. So let's organize what we know about the paper readers. How many paper readers were there total? Okay, so total is 630. The juniors are 215. So how can I find the seniors?
Subtract.
Yes, just subtract them. Okay, so then that's going to be the amount of seniors. Okay, so we're going to do 840 plus 630 minus 415 to get our numerator. Now, if it doesn't tell you how to write your answer, I do want you to write them both as a fraction or as a fraction, but this one, when they're bigger numbers like this, I'm going to have you write it as a fraction and as a decimal, because if they're larger numbers like this, it's most likely I'm going to ask you to write it as a decimal instead of reducing them, even though, what do we know goes into both of those? 5. So we're just going to divide by 5. To get 211, 1560 divided by 5, get 312. Okay, and we know 3 doesn't go into this one because 2 plus 1 plus 1 is 4. So this is going to be our fraction, and then we're just going to find our decimal. So this is going to be 0.6, and then the 7 gets rounded up to an 8. So that will be your final answer. Alright, so based on what we did for this one, we do have to change the name of these examples. So this should say 4, 5, and 6. Okay, I'm going to give you the values, and I want you to set it up just like the last one, okay? So of 160 beauty spa customers, 96 had hairstyling, and 61 had a manicure. There were 28 customers who had only a manicure. What is the probability that the customer had hairstyling or a manicure? So the probability of hairstyling, we're just going to shorten manicure to mani, minus the probability of style and a man. Alright, so let's see if you can do those calculations. All right, so when you're finding the probability of the hairstyling, it's everybody who had a hairstyling. So how many people had that? 96 out of the 160 customers. For the mani, it's everybody who had a mani. So how many total manis were there? 61, okay? So when you're doing the probability of the mani, you have to include everybody, including ones who got both. Okay, so when you do the subtraction, set it up the same way we did before. So you're going to do the ones who had manicures, so the total number of people who had manicures. Okay, and then the ones who only had manicures is 28. So the ones that had both, how do you find that? You just subtract it. 33. Yep. Okay, so if you know the total and you know the ones that only had a manicure, you can find the ones that had both of them. Okay, and then when you calculate that, you should get 124 over 160. So 2 goes into both. Do you guys think there's a higher number that goes into both? Yeah. So 124 divided by 4. 31, and then we know 16 divided by 4 is 4, so this is 40. Okay, and then we're going to divide. So 31 divided by 40. I'm fine if you want to keep this exactly as the 0.775. It doesn't say where to round, or you could also round it to 0.78. Alright, now the next concept we're going to learn is going to use the complement, which is something that we talked about earlier in this unit. Okay, so it says each of 6 students randomly chooses a butterfly from a list of 8 types. What's the probability that at least 2 students choose the same butterfly? So I said circle the important numbers, underline the question. You can also highlight the question. So what we want to do is we want to find the probability that at least 2 students choose the same butterfly. Okay, so there are 6 students, okay, and there are 8 types of butterflies. Okay, so the probability that at least 2 choose the same is equal to the whole, which is 1, minus the probability that everyone chooses differently. Okay, we are going to learn in the next chapter how to do the probability when at least two choose the same. It's a little more complex than what we're doing today. So 1 minus the probability that everyone chooses differently, we're going to set up a fraction that's going to be similar to something that we did earlier this week. So if there's 6 students, I like to line up 6 spaces. And for the total, that's the total options. So the first student has how many options? 8. The second student still has 8. Okay, so all the students are choosing out of 8 butterflies. That is your total, okay? So we can really just write that as 8 to the 6th power, okay? And then when you're finding the probability that everyone chooses differently, that's your favorable outcome. So if we're finding the probability that everyone chooses differently, the first student has how many options? How many choices of butterflies? 8. But if we're saying that everyone chooses differently, then the second person only has how many choices? 7. And then 6, 5, 4, 3, and then I stop at 3. Why? There's only 6 students. Okay, so if there were 7, then you would go down 1 more. All right, so we're going to do 1 minus that value. Okay, and you can do this a few different ways. You can calculate this first. Oops. Times 1, there we go. Okay, and then you have 1 minus 20,160 over 8 to the 6.
Why did you multiply that by 1?
Because I put a extra times in there. My calculator didn't like that, so instead of deleting it, I just wrote times it by 1.
Okay.
Anything times 1 will just be itself. And then we're going to divide. So if you stop there, like you should have, then you'll get the same thing. And then you can just do 1 minus, and then we can put in our fraction. So this would definitely be one where I would ask you to write it as a decimal. Okay, so then this is going to be approximately 0.92. And if you wanted to get the fraction first, you could also do that. You could just take the denominator minus the numerator. So this is what you're calculating, the 241,984 over 262, 144. You get the same thing. And you don't have to do that. You can just do all the 1 minus together. All right, so based on that, I want you to do example 6. So in one day, 5 different customers bought earrings from the same jewelry store. The store offers 62 different styles. Find the probability that at least 2 customers bought the same style. Okay, so it's almost the exact same setup. Feel free to check in with your elbow partner. And then when you're done with that, we get out your 7-4. Okay, that page is 7-4. All right, let's make sure we set this up. So there are 5 customers, okay, and we want to find the probability that they're all different. So on the bottom, 62 to the 5th power. There's 62 times 62 times 62 times 62 times 62. And And then when you're going through on the top, remember, the first one has all 62 choices, but then once they pick one, the next customer only has 61, and then 60, 59, and 58. Okay, and then when you're like showing your work, just having this step is fine, and then if you want to do the rest in your calculator, you can. Okay, if you didn't get the final answer of 0.15, then it would be a good idea to check to make sure that you got these numbers. Make sure that you put these in the appropriate parentheses. Sometimes I like to do these out, but those are pretty large numbers there. So you should get the 0.15. How'd you do? Got it? Rounded correctly?